Good evening, and welcome to week 9 of the live sessions for the fundamentals of additive manufacturing technologies. It is 6 p.m., but participants are yet to join, so we will wait for a few more minutes before we start. Thank you. Good evening and welcome to week 9 of the live sessions for the course Fundamentals of Additive Manufacturing Technologies. This course is taught by Professor Sajjan Kapil, who is faculty in the Department of Mechanical Engineering at IIT Guwahati, and I am Sourav Goswami, a PhD candidate in the Department of Mechanical Engineering at IIT Bombay. In the past week, the lectures focused on wire based additive manufacturing processes, and particularly for this week, Professor Kapil spoke at length about beam-based energy processes. So, either an electron beam-based wire additive manufacturing process or laser beam-based wire additive manufacturing process. In the weeks prior, we did take a look at arc-based manufacturing processes also. So, as with our usual classification of the additive manufacturing processes based on the subcomponent and subsystem levels, we would be speaking about metallic wires, and they typically flow continuously. No drop on demand type systems are known to commercially exist. The kinematics, again, is a choice of the manufacturer or the designer. And the energy source that we'll be focusing on for this week is beam-based systems. So this, and first we'll talk about electron beam-based AM processes. Now, as we know, electron is among the lightest of the subatomic particles. Its mass is only say 9 into 10 power minus 31 kgs, and it has a very small charge of minus 1.6 into 10 power minus 19 coulombs. And of course, the question which would emerge in many of our minds is if uh, how does such a light and a lightly charged particle transfer energy to the material and enough energy to melt it, and that happens through its kinetic energy. That is, because of it being so light, it can be accelerated to great velocities, almost two-thirds the speed of light. In fact, here in this plot, it says that for sufficient accelerating voltages, say up to 10 to the power 5 or 10 to the power 6, we can almost achieve or 10 to the speed of light, never quite reaching it, but that is a substantial number. And as we saw in this video, often the movement of this electron beam over the powder surface is so quick, it appears that there are multiple beams that are acting simultaneously, whereas there is only one beam which is scanning the surface. And here are summarized some of the typical electron emission methodologies. Of course, the most commonly used ones are thermoionic based and plasma gun based. So in a thermoionic system, okay, so fundamentally for to emit or produce electrons from any solid state material, we will have to provide it with some energy. And this minimum critical energy is equal to the work function or potential barrier for that specific material. For the thermionic emission, this energy is provided in the form of heat, and upon sufficient heating, electrons get liberated from the target surface. In the case of photon-based emission, the energy is transferred in the form of photons, so similar to our lasers, and impingement of this energy leads to the emission of electrons near the surface of the target. We may bombard a surface with secondary electrons, and with electrons, and bombardment with electrons may lead to the formation or expulsion of other secondary electrons from the conduction band. There may be ferroelectric modes, and there is plasma. Plasma, as we discussed during our session on arc-based processes, occurs when a gas is heated up. Upon heating sufficiently, it will segregate into ions and electrons. And given that the plasma already does contain these electrons, the only task left to us is to bring them out. And that is often done by providing a positive voltage bias, which attracts or pulls out these electrons. For metal processing, by processes such as welding, lithography, or even for microscopy or AM, typically thermionic and plasma emission based processes are very popular. And specifically for thermionic emission, Richardson's law may be used to calculate the current density given the material constant. Okay, not even this is a constant for all processes. Given that absolute temperature of the emitter, the work function for the material, we may be able to calculate the current density that can be expected. Among these two, that is the thermionic based processes and plasma based processes, there are certain advantages and disadvantages. This slide presents a comparison of both. However, in either case, there are certain stages. So first, of course, is generating the electrons. But as I've been mentioning, these electrons, even though they are liberated, are often concentrated near the surface of the emitter. So maybe somewhere here. And they have to be accelerated and moved towards the target surface. Now, once they are uh, liberated, they are accelerated using electrostatic coils. And again, this is typically achieved by providing a positive bias, as we see here, to the anode, and that pulls out the electrons because of the attraction of opposite charges. However, this beam may diverge upon accelerating, and to focus it and deflect it, we typically use some magnetic coil, which uses magnetic forces to direct the beam of electrons as per our requirement. For the plasma gun based systems also, the analogy is similar. There is a discharge voltage and there is an accelerating voltage. Discharge voltage again is used to bring out the electrons from the system, and acceleration voltage accelerates them towards the target surface. Commercial systems by RCAM and Seaki use thermionic electron beam guns, whereas the company X-beam uses a plasma electron beam gun. Now, typically, plasma gun has current density which is, say, up to one order higher than thermionic guns, and the requirement for acceleration voltage is also lower. For thermionic guns, you need acceleration voltage up to 150 kilovolts, whereas for plasma guns, only up to 30 kilovolt is sufficient. Again, the requirement of vacuum in a thermionic gun is higher, up to the order of 10 to the power minus 9 bar. This is similar to the amount of vacuum that we typically require in the gun chamber of, say, an ESEM or scanning electron microscope. Whereas for plasma gun, the requirement of vacuum is on the lower side, only up to 10 to the power minus 5 bar, which is typically the amount, the extent of vacuum which you require in the working chamber of an SEM. Again, thermionic guns have shorter lives because of the high temperatures to which the emitter is exposed, whereas plasma guns tend to last longer. Also, plasma guns are cheaper because of the ease of usage and the requirement for low vacuum. Now, as we were discussing, typically an electrostatic field is used for the extraction and acceleration of electron beams, whereas magnetic fields are used for focusing, deflecting, and correction. The interaction of a charged particle with the electric field, which produces some accelerating forces on it, given by the Lorentz equation, is also shown here. From the cathode, to the anode, cathode being our say emitter. Focusing is done by electrostatic forces, and further away from the anode to the target surface, the focusing and deflection is done by electromagnetic forces. In the first stage, focusing magnitude of the electron's velocity increases due to electric field, and in the second stage, only the direction changes while the magnitude remains constant. In both stages, they are getting accelerated. In the first stage, the velocity is changing because of the change in speed as well as direction. In the second stage, only the direction is changing. The speed is more or less constant. Also, here is a helpful equation which helps us find the focal length based on the charge of the electron, the strength of the magnetic field, and the acceleration voltage. Another question which might arise is what is the use of an electron? What is the use of vacuum in an electron beam gun? Because we mentioned how for thermionic guns we need a high vacuum of the order of 10 to the power minus 9 millibar. For plasma guns also, it is needed to be of the order of 10 to the power minus 5 millibar. That is because electrons, as we know, are very light particles. Thus, if while in motion any other molecule which would typically be heavier than electrons should come in their path, they would get deflected very easily. And rather than reaching the target surface, they would get scattered. So they have to, the only way to ensure that there is a obstruction free path from the emitter to the target surface is by uh, creating a vacuum in the working space. Another reason is that for thermionic guns specifically, the emitter is subjected to very large temperatures. And as we know, with increase in temperature, the tendency for corrosion shoots up drastically. So, to prevent our emitter surface and to elongate the gun's life, we should maintain vacuum so that the chances of corrosion are minimized to the extent possible. Based on the amount of vacuum required, different types of pumps are used, and typically they are used in conjunction with each other. So rotary pumps are sufficient for providing or reaching vacuum from the ambient conditions to 10 to the minus 2 millibar. So somewhere over here. Root pumps also operate in an overlapping range. However, they cannot operate right from atmospheric pressure. Now, this is where diffusion pumps take over and turbomolecular pumps as well. However, both have slightly different working mechanisms as well as slightly different targets. So the working mechanism of a rotary pump is illustrated here. I'll just enlarge this. The first stage is suction. So it will suck out the air and gases from the target area or the working area. We see that this other nozzle is currently closed. Now once the air has been sucked out in one cycle, it will be transported to this other side, and this is a spring loaded lever which is available here. In the third stage, the pump will begin to compress the air which is it has taken up, and in the fourth stage, because of the pressure buildup, this valve will open up and the air will be or the gases will be expelled to surroundings. Root pump operates in a similar fashion, except rather than a spring-loaded lever, it has this lobes. We see that the rotary and the root pump are connected to the working chamber, where the requirement for vacuum is of the order of 10 to the power minus 5 millibar. Also connected in series is this diffusion pump. And how the diffusion pump functions is that there is some oil, which in typical technical terms is just called DP oil, that is diffusion pump oil, and there's a heating element. Now the oil is heated and it forms vapors. And what happens is the air from the working area is pulled into the pump, and then the molecules of air are this oil adsorbs on the surface of those molecules, making them heavier. Now, once the molecules become heavier than typically in air, they are pushed over to this diffusion, a rotary pump and root pump, and then the rotary pump and root pump can expel them into the surroundings. However, even though this can achieve vacuums that might be required near the gun chamber also, we see the obvious problem that the presence of these oil particles or oil molecules in the atmosphere may interfere with the functioning of the heating element. That is, this oil may also adsorb on the surface of the heating element, affecting its functionality. Secondly, because these oil molecules will be suspended in the space, they may interfere with the motion of the electrons and may contribute to its scattering. So diffusion pumps cannot really be used in the gun chamber. And that is where typically you use these turbomolecular pumps. In turbomolecular pumps, you have a combination of stator blades whose function is to guide the particles, and moving blades or rotary blades which provide kinetic energy to the particles. Upon interaction with the moving blades, again, the air particles are passed on to the backing pump or the rotary pump, which can then expel it to the surrounding environment. So here might be, this is the beam generator, so this is the gun area. Here you require vacuums of the order of 10 to the minus 9 millibar. And that is where the turbomolecular pump is used. But ideally, in a system, you will have all of these which operate in conjunction. This is a video which shows how electron beam based wire beam additive manufacturing has been used to make really large parts in a single go. This process is fast and has good build rates. However, because of the high deposition rates, often the finish is compromised, and any post-processing steps such as surface milling or end milling, face milling become almost say unavoidable. Again, it is interesting to see how the beam interacts with the material that is to be deposited and the surface of the substrate. So just like in the previous case, where you could have a droplet transfer or a bridge transfer or stubbing, something similar can be observed here, where based on the interaction of the electron beam with the filler material, either depending on how far away this wire is from the surface, which is quantified by this parameter h, the droplet can form and keep growing in one spot unless until finally it becomes too heavy and falls down, spattering onto the base material and the melt pool which forms here, or it can be brought close to the substrate or pre-built layer such that it melts and fuses with the melt pool almost simultaneously, leading to a bridge transfer. Or in the reverse case, if we bring it too close, we may also end up stubbing the wire into the melt pool. Of course, this will be dictated by the interaction of the various forces, one of them being the force of gravity, which is the body force. Then you have this electron beam pressure force. There is a beam of electrons coming from the top, which strikes this droplet as well, pushing it downwards. Then you have the metal vapor jet force. That is because of melting and evaporation in this region, the fumes will rise up, metal fumes, and these metal fumes will also interact with the droplet, trying to force it upwards. Then you have the surface tension on the droplet surface, which tries to pull it up along the filler material, which will also have a component in the vertical direction. So if you're seeing just in the vertical direction, the forces are the force of gravity, the force due to the electron beam, the force due to the metal vapor, and the component of the surface tension force. The formula for all of them are given here. And when we equate this for the steady state, we end up with the critical radius for the droplet, the radius is coming into the picture because the metal vapor force is a surface force and interacts only with the droplet surface. It's not a body force. Thus, the R term comes in, and this critical an expression for the critical radius of the droplet is obtained here. This can help us demarcate the exact size to which a droplet can grow before it becomes too heavy and falls down or spatters into the melt pool. The critical condition for metal transfer, which decides the transition from, say, bridge transfer to droplet transfer, is given by this height parameter h being greater than or equal to twice the radius of the droplet. Similar to other additive manufacturing processes, electron beam based wire beam AM processes also come with a certain set of challenges. One, of course, is residual stresses and distortion. Residual stresses we have already spoken about at length, and we saw how compressive residual stresses may prove useful, whereas tensile residual stresses are dangerous. Also, here you can see the extent of distortion of this plate. So I'm just drawing the outline of the plate. We see how much it has curved, whereas typically it should have been flat, something like this. This distortion is very apparent on the build plate, but it would have also happened on the deposited part itself, which would lead to significant deviations from the design geometry. Another concern is the surface finish. As we discussed, because of the high deposition rates, the surface finish is often compromised and post-processing machining steps become unavoidable. Support materials cannot be added easily because of the difficulty in their removal, and thus either we stick to very simple prismatic geometries which have no overhangs, or we use a multi-degree of freedom table, such as a five axis table. Again, because of the high energy involved and because of the formation, melting and vaporization of the metals, certain elements can be selectively evaporated, which would mean that while your feedstock had one particular material chemistry and composition, the final deposited part has a different chemistry because of the selective evaporation of certain materials, and thus there is a change or detriment in the mechanical and metallurgical properties. Another problem is the problem of omnidirectionality, which we also looked at while discussing TIG-based AM processes, where depending on the type of feeding and depending on the traversal of the deposition head in conjunction with the feeding apparatus, the type of feeding may change from front feeding to side feeding to back feeding and so on, leading to anisotropy in the material properties. Another very interesting aspect which has been pointed out here is that the electron beam, which is used for deposition and melting, may also be used for metallurgical analysis of the build part. As we know that in scanning electron microscopes, we bombard the surface with energetic electrons, and then based on the interaction of the electron with the material, and based on the secondary signals which get activated, we are able to gain information about the material's topography, chemistry, about its surface, and so on. Thus, the beam of electrons, which is already available here, may again be impinged at a lower energy to extract useful metallurgical information. Sometimes the electrons which may reflect from the surface during the build cycle itself may be caught by certain detectors in situ during the deposition process and may be processed further for extracting useful information. So omnidirectionality is a concern, and typically we want to achieve omnidirectionality so that irrespective of the tool path, and irrespective of the direction in which we must build our parts, the metallurgical and mechanical properties remain more or less isotropic. One solution is the centrally fed feedstock, where a wire is coming from the center and the electron beam surrounds it from all sides. So, multiple equally spaced oscillating electron beams. Why oscillating? Because typically your beam will be very fine. Okay, maybe red was not the best choice of color. Typically your beam will be very fine, but because of the high speed with which it can be deflected and because of the very lightweighted nature of the electron particles, we can deflect it at great speeds so that it forms this curtain of energy, so that it almost appears not like a thin beam but like this hollow cone of beam. And this results in a heat intensity distribution which is somewhat similar to an annular laser beam profile. Alternatively, also a hollow electrode can be used, such as shown in the figure on the right. So in one case, you had three discrete electron beams contributing to omnidirectionality, and in the other case, you only had one beam which was splitted or made hollow into a donut-like shape, annular shape. We see that such electron beam-based processes have already been put to use and are extensively tested and developed by NASA of all agencies, and they present a very interesting frontier of research, and it is an upcoming technology which is very promising. The next set of lectures were on laser beam based additive manufacturing processes. Here again, the wire material that we worked with was metallic. The material flow was continuous, so the wire was simply extruded through some pinch roller like mechanism. The machine kinematics is the choice of the manufacturer or the designer. The energy beam is a laser beam. Again, either we build simple geometries which do not require supports, or should overhangs be present, we need to use a multi-axis kinematics table or a robotic arm. Robotic arm and a multi-DOF table also differ in certain aspects, which we had discussed in the previous weeks. This is a generic schematic of a robot or robotic arm based uh, wire laser beam additive manufacturing process. This is the laser unit, which will typically have a chiller, a lasing unit, a UPS also, and the laser is then delivered to the deposition head via an optical fiber. The optical fiber connects to the deposition head, which is mounted on the head of the robot. There is also a constant flow of argon gas to shroud the melt pool from neighboring atmosphere, and also to protect the laser optics. A wire feeder is used to feed wire into the metal deposition head, and it is extruded using a pinch roller assembly or a similar mechanism. Often, rather than installing a dedicated robot, the deposition head may also be retrofitted to an existing 3-axis or 5-axis CNC machine. And the added benefit which this offers, apart from the savings in cost, is that based on the configuration, you may be able to develop a machine which now has hybrid capabilities. That is, it can perform both additive as well as subtractive processing of materials. In this case, again, the laser unit remains more or less unchanged. And typically these days, it would come as an integration engine. So you have this engine which has this lasing unit and a controller of its own, along with a chiller, UPS, and similar things. Then, via an optical fiber, the laser beam is delivered to the deposition head, which is retrofitted on the head of an existing CNC machine. You couple it with a wire feeder, which again is assembled manually, and mount it to the side or top of the machine. You connect it to an argon gas supply, and voila, you have an laser beam based wire beam additive manufacturing machine. Now, typically, a laser wire cladding unit can either be omnidirectional or direction biased or unidirectional. In the cases where lateral wire feeding is used, such as shown here on the left, the omnidirectionality is lost because, as we can very well see, depending on the change in traverse direction of the laser deposition head, the type of feeding can be front feeding, back feeding, or either side feeding. Whereas for the omnidirectional case, certain explored and say commercial designs are already shown here. One is a rotating feeder type design, one is this annular beam, and one is the slit beam type of design. Here we also see some images of robot arm based uh, wire laser additive manufacturing machines. The first has a lateral feeder, so the one shown here, wire comes from the side, and this appears to me as source of argon gas, and the laser is coming from the top. On the other side, we have a rotating feeder, where to ensure omnidirectionality, the head or the deposition is mounted on a rotating assembly so that omnidirectionality can be preserved. And typically for wire additive manufacturing, it has been observed that front feeding tends to give the best results. In some cladding applications, back feeding is preferred. Again, for such lateral mounted systems, schematic is shown here where the wire is being fed from a side. The laser may also be at an angle to the normal. They are not generally not aligned normally. So you see this small angle beta, which offsets the laser axis from the true vertical. And this is to prevent the ingress of any reflected laser energy back into the laser optics. So we know that the typically the angle of incidence equals the angle of reflection. If the laser beam were to fall normally on the surface, and especially if the surface is highly reflective, as is typically the cases for metals, there is a chance that some energy will be reflected back, and that reflected energy can in turn damage the laser optics. Laser optics are very fragile and costly, and so we would like to preserve them and prevent any sort of damage whatsoever. However, tilting by just this small angle ensures that even if there is some reflection, it will occur, say, at an equal angle to the normal, so at an angle beta, and it will avoid the laser optics. So a simple configuration such as this, which has little feeding, may still be useful in the case of rotary components, where say this cylinder will rotate, and this part is being cladded on top of this rotating assembly, because in this case the deposition is anyway unidirectional, and omnidirectionality does not come into the picture because of the simple tool path. With a rotating tool, rotating leader, we get rid of the problem of say anisotropy. Why is my please give me a minute. I think my screen. Oh yeah, it's fine now. It was frozen for a minute. Yes. So depending on the relative positions of the wire as it is entering the melt pool, it can start melting either at the leading edge, so somewhere here, and get deposited there itself. It can melt near the center of the melt pool and get deposited here, or it may be fed in such a fashion, such as for instance at high speeds, so that to accumulate the amount of energy required for melting, it takes a time by which it has already traveled through the trailing edge. As we know, based on the direction of travel, the melt pool is not really symmetric. It has this long tail and a short head. and the fluid flow. So if I just draw one melt pool, the top view of a melt pool, and if this is the center of the laser beam which is falling, the more typical movement of the fluid will be towards the back and towards the front as well. Of course, there are other factors such as Marangoni convection, the presence of surface active elements, and so on. But the point I'm trying to emphasize is that the melt pool shape on the surface is not symmetric. So, depending on there's asymmetry already present. And again, if the wire is entering at different regions, the characteristics of the bead can be very different. And for best results, we want the wire to melt near the surface, near the center of the melt pool, as that is the hottest region and that has the least, say, surface movement of the fluid. Of course, there are internal convection, and the melt pool also tends to be deepest, right under the laser beam. So this can ensure optimal dilution and good bonding strength. Now, when the direction is reversed, the scenario of deposition, whether it is happening at the leading edge, at the trailing edge, or near the center, may also change. And this is where the rotary feeder type mechanism comes to the picture and helps us. The beam can also be shaped into an annulus to get rid of the problem of the lack of omnidirectionality. And in this case, first we have this composite beam, which has a TM00 profile. Then it goes through an optical device called an axicon, and this axicon transforms it from a TM00 to this annulus shape. However, this itself is not sufficient, and we want to further bifurcate this or bisect this into two C sections. That is performed accomplished through this prism shown here. So now you have a bisected beam and you can feed your wire through this region. Once the wire is fed, we want to join this beam again, and we use a reverse prism, that is the second prism here. And finally, you end up with a donut-shaped beam as given here. Further, this donut-shaped beam is then converged onto a single point or onto a small region on your intended focal point. And this has been commercialized by Precitech. However, the previous system involved a lot of, say, complex optics and optical arrangements, and the head was also be pretty big and fragile. A simpler approximation is just using these, uh, say, splitting the beam into three or four beams, and then again fusing them together on the target surface. And this is type of system is shown here, courtesy of Fraunhofer. So here you may have a set of splitting. You may split the beam into say three or four components. So and then you have this mirror arrangements, which are then used to focus them back into one spot. And this diverging section is what you expect to feed your material into the system. Now these are the process parameters which are typically involved in any laser metal wire additive manufacturing process. And as we see, there are a lot of them, and that is one of the reasons why analysis of such processes is so difficult. It's because there are so many variables. This is also why often the reproducibility of and the consistency of such processes is questioned, because not all variables are in our control and some may change inadvertently. And even small changes in these process variables tend to produce pretty significant changes in the final material properties. However, there are a few parameters which we actively control. One of them is power. The others, which dictate the thermal energy, such as the beam dia, the beam profile, and the wavelength, are fixed once you have bought a laser system. The working distance can be adjusted, but often you have an optimum number and you don't want to fudge around with it too much. Typically, you'll work at the optimum working distance. So this can be changed, but typically the need does not arise. Apart from academic research, where you want to see the effect of changing this working distance. The next set of parameters relate to feeding. So the feeding direction, the feeding position, the feeding angle, which again are a function of your feeding system. Typically, we do not change these very often and they are mostly fixed. The gas flow rate, while it is a parameter which can be controlled actively, often you have like a cutoff value, say 10,000 or 10 liter per minute, 10,000 milliliter per minute to 30,000 milliliter per minute or 30 liter per minute is a good number for printing using such processes. The wire feed rate, however, is a parameter which we can actively change to influence the deposition rate as well as the type of bead that is getting deposited. The design parameters, such as the material of wire, diameter of wire, and material of substrate, are changed often because based on the type of job that you want to print, you will be changing these parameters. The substrate geometry is mostly flat, and the feature geometry will depend on your design or on your job. The motion and path variables, such as the scan speed, is uh, say optimized. As we saw previously, we use a single track experiments, then single layer multi-track experiments, and finally multi-layer multi-track experiments to optimize most of these parameters. Similarly, the scan speed is also optimized. It may be changed depending on the accuracy and the build rates that you want. Similarly, for this track overlap ratio or the step over, the deposition path or the tool path, the interpass time, that is if you want to introduce any cooling time between two successive layers by increasing the delay, and any preheating temperature, which will help you to get rid of the type of distortion that we saw in one of the previous slides. And here are the typical ranges of these parameters. Typically, the type of lasers which are put to use are diode, disc, ND-YAG, and fiber lasers. CO2 lasers are not used so much, typically because of their wavelength, which is of the order of 10,000 nanometer. These do not interact with metals very well. However, they may be useful for ceramics. Diode lasers, the order of the wavelength is mostly say 1000 nanometer. So anywhere from 970, 980 to 1070, 1080 nanometers. Typical powers, which are used in commercial machines, range in the order of 1 to 20 kilowatts. The deposition rates can be between 1 and 50 grams per minute. Their thicknesses are typically above 1 millimeter, and that is because, as we know, we typically use the your normal simple welding wire for these applications, which typically come in thicknesses of say 1.2 or 1 mm. The wire dia, even though it says zero point 0.2 to 1.2 mm, typically you will not use anything below zero point 0.8. It is because welding wires are typically available in those configurations. The bead width can be anywhere from 5 to 15 times of the wire diameter. However, this can be controlled and tuned further. The surface finish often is 40 to 60 microns. We know that mirror finish is what, around 1 micron or lower. So we can imagine the type of surface that you get. The traverse speeds can be as high as say 2000 or 2500 mm per minute. And typically these processes may be used for repair, for feature addition, for surface treatment, and by cladding for surface protection. The deposition characteristics change depending on the laser power, the scanning speed, and the wire feed. which are used in the process. And depending on the combination of these processes, you can have a wire dripping type of material deposition or droplet transfer deposition, which occurs when the available energy is too high and melts the wire prematurely. The wire tip melts much before the point or close to the point of intersection with the melt pool. It is usually observed when the wire feed is excessively low for a fixed combination of traverse speed and laser power. Of course, typically, how we optimize these parameters is we'll keep two parameters fixed
Excuse
and
me, sir.
vary the third.
Sir, the
Hi,
screen
Kiran.
is not visible, sir.
Is there some issue? Please allow me to reshare. Um, Hello, can you see now? Kiran, could you please confirm if the screen is visible now? Okay, so I see the screen in my meeting. I think it is visible and will continue. Yes. Typically, how you optimize a parameter is that you will fix all others and vary only one parameter and see how it is affecting. Often with experience, you can come up with certain ratios of the parameters, say the ratio of wire feeding and traversal or the ratio of power and wire feed. So you have some basic idea of what is, say, the general window within which you can expect a good deposition. And of course, those are further refined with, say, optical and microscopic characterization. The droplet transfer type mechanism may result in discontinuous traps. Here, while the continuity is preserved, we see these surface artifacts, that is, in some regions, the material has bulged. Then there is a region of low deposition or under deposition, and then it has bulged again. This is because the wire feed rate is too low and it is not able to keep up with the traverse speed of the deposition head. The opposite case is that of wire stubbing, where the wire feed is too high. Because of the very high wire feed rate, the available energy per unit time per unit length is low, and hence the wire enters the melt pool in an almost solid or semi-solid form, resulting in collision of the wire tip with the solid substrate at the base of the melt pool. Such a collision results in the wire tip moving away from the center of the melt pool, such as may be seen by these spatter-like signatures here. And in this case, the wire does not remain solid for long because of the energy which is present in the melt pool, which melts it. However, the tracks which solidify have an irregular shape, which is highly undesirable. And as we discussed, typically occurs when the wire feed rate is too high. The optimum case, of course, is the one of bridge transfer, where your wire feed rate and say laser head traversal speed are well synchronized so that the melting occurs very near to the melt pool, such that the droplet forms and immediately gets say deposited inside the melt pool, forming almost a continuous chain or a bridge. And this leads to these very smooth type of beads. Often another type of defect which you will see is because of the process instabilities at the start and end of the revision process. In the beginning, there might be some bulging or balling, and in the end, there might be some over or under deposition. But the intermediate region or the middle region is smooth. Also, typically, it is said that it takes around 3 mm for any melt pool to be stabilized. And after this length of 3 mm, we may expect to see It's a continuous and smooth weaves. The wire deposition characteristics are often studied under the purview of the energy densities, which may either be a linear energy density or energy per unit length, and area energy density or energy input per unit area, or a volumetric energy density, that is the volume input per unit, the energy input per unit volume. For the simplest case, that is energy per unit length or linear energy density, it is given simply by the ratio of the power in joule per second or watt and the traverse speed, which is typically in say millimeter per second or millimeter per minute. And the units you end up with is joule per ml or energy per unit length. The deposition volume per unit length in millimeter cube per millimeter has traverse speed Vt and wire feed rate Vw as a determining variables. The amount of volume which is getting extruded per unit time, as you know, is the cross section area of the wire times the wire feed rate. This divided by the traverse speed of the head is the amount of or the volume of wire or bead that you're depositing per unit length of the track. Based on multiple experiments, by varying all of these parameters, you can come up with these working curves or process maps, which help may serve as a ready reference to determine what may be the optimum process window when you want to build a part or deposit few layers. And here is a very useful equation for calculating the critical power or the minimum amount of power which may be needed to melt both the wire and the substrate. So here the energy is divided between the two. For the wire, this is the first part. This is for the substrate. Typically, your wire and substrate may be of the same material, but in certain applications and increasingly so, the wire and the substrate or the wire and the feed deposited material may be of uh, maybe different materials, and so even the thermomechanical constants will change. These thermomechanical properties themselves are again a function of temperature, and often to make your calculations more accurate, it may be a good idea to incorporate temperature-based relationships for each of these properties. Also, very interestingly, typically here a typical number for the efficiency of laser absorption is given as 70%. This is a function of both the material property, that is the material, the temperature at which we are working, and the wavelength of the laser. So the absorptivity and reflectivity will change with the wavelength, as well as with the surface finish, as well as with the temperature. So with increasing temperature, typically for the same wavelength, the absorptivity increases. That is why when we are working with materials such as aluminum or copper, uh, it is typically recommended to preheat the material because it improves the absorptivity. For aluminum, you may have to work with a different wavelength because it does not, it has poor say absorptivity and high reflectivity at your typical 1000 nanometer wavelength. For copper, preheating may just do that. And finally, we move over to processes which use powders as the raw feedstock. So powdering and such powder-based additive manufacturing processes may have the powder either in the form of a bed. So you have this build chamber, a stage similar to your VAT photopolymerization, and in each pass, this layer of powder is deposited on top. Of course, underneath you may already have been building a part, so maybe something like this. and there may be a roller arrangement or some other which moves over and spreads a uniform layer of powder on the surface, compacts it, and you have a laser beam which scans the surface, prints your part in this layer. Or you have a powder feed type additive manufacturing process where there is no bed, there is just a substrate or a pre-deposited layer, and you are uh, depositing the powder in real time. So these are called directed energy deposition process. So powder based or blown powder, directed energy deposition. Today we'll be talking about powder feed additive manufacturing processes, but for the bed based processes also, it may either be a binder based powder bed where you are say selectively depositing binder drops on the powder bed, and wherever those drops fall, the material gets cured and forms your part, such as for the case of cement, water may act as the binder particle, or energy beam based processes where you scan the surface of interest or the region of interest with a laser beam or an electron beam to selectively melt or sinter the particles together. So for the case of laser beam based processes, you can have selective laser sintering where you're not really reaching melting temperatures, but you are reaching say zero point 0.6 to zero point 0.8 times the melting temperature, which is sufficient for sintering and joining of the particles. But it is still a mostly what it is a solid state process. Or you may opt for selective laser melting, where the temperatures are sufficient to melt the powders entirely and fuse them together. DED might be one of the most commonly used terms for such processes, but there are others which are equally popular, such as direct laser deposition, laser consolidation, lens or laser engineered shaping. This is a trademark of Optomic, direct metal deposition, 3D laser cladding, and many others. Just like most other AM processes, this also has a pre-process, build process cycles. What additionally can be done is the addition of certain in situ processes, like we have been talking about, such as further relieving of residual stresses. We can have a short peening or a hammering or an in situ rolling step, or we may have some in situ diagnostics and in situ monitoring setup, such as a thermal camera, which can give us updates about the process in real time. The build process itself consists of the creation of a small melt pool by using a focused heat source on the surface, then injection of build material into this melt pool, and here we'll be talking about powders, then the generation of a synchronized motion of heat source, material injection, and substrate to develop the desired part geometry. Now, a typical powder feed based system uses powers up to 10 kilowatts. A focus beam falls on the substrate, creates this molten pool, and inside this molten pool, the powder material is injected to get melted and deposited. The powder material also interacts with the laser in its path. So it takes some energy from the laser, some energy from the melt pool, and then melts. The exact dynamics and interaction will be looked at in the subsequently. Typically, an inert shroud gas, such as argon, helium, or in certain cases nitrogen, is used to shield the melt pool from atmospheric oxygen. This also improves the layer by layer or layer to layer addition by providing better surface wetting. Typically, your powders which are used in these processes may also have undergone a process such as gas atomization or water atomization. For gas atomization, depending on whether nitrogen gas was used or argon gas was used, there might be certain uptake of these gases into the particles, which may then reflect in their material chemistry and their metallurgical and mechanical properties. The part is built on an XY table placed below the deposition so that the laser and power head can move on it in a raster fashion or any other tool path as you desire. After a layer is built, the distance between the laser beam and the substrate is increased by the desired layer thickness. This can be achieved by either having the Z motion on the deposition head and the XY motion being on the table, or all three motions being on the table and the head being stationary, or any combination of motions being available with either the head or the table. While fabricating features or assembly components require deposition in planar layers, and thus we typically use these flat substrates, the laser beam powder delivery head can also be tilted using either a 5-axis CNC or a robotic arm, so that we can deposit overhangs in a fashion such that the beam axis is normal to the deposition field. Of course, such processes are built upon the original advancements made in the field of laser cladding, which was originally developed for the surface treatment of parts, with the objective of improving their wear properties or corrosion properties. And typically, what you wanted to do is on your existing material, you wanted to coat a layer of a stronger or different material. In this case, the powder was blown by argon gas and delivered towards the molten pool created by a laser beam. And thus, this technology is not compatible with electron beam based energy sources. Why is that? It is because of the constant inflow of this argon. As we discussed, for electron beam based processes, we require vacuum, which ranges between 10 to the power minus 5 millibar for the working area to 10 to the power minus 9 or 10 to the power minus 10 millibar for the gun chamber. By this influx of argon, that vacuum will be lost, and thus the electrons will interact with the argon gas and will get scattered and will not uh, transfer energy to the intended deposition area. A typical powder-based DD setup has these components. It will have a powder metering unit, which supplies the requisite amount of powder to the deposition head. There is a powder conveyance and shield gas in it, both consisting of argon gas. In case multiple powders are used, there may be a mixing chamber, which produces a homogeneous or, based on the requirements, stoichiometric mixture of the two powders. Then there is the powder delivery and optics module. The powder materials may be metal, polymer, or ceramics. Powder handling system typically consists of a metering section, a convening unit, and a delivery unit. And the machine tool type, as we discussed, can either be a CNC machine, pre-existing CNC machine, also which the head is retrofitted, or it can be a robotic arm. The types of metering and conveyance and delivery units are listed here. First is the screw-based or auger method-based metering and conveying systems, where you simply use a screw for measuring the amount of powder which is transmitted and transported with the motion of the screw ahead. This was one of the earliest techniques which was implemented in as early as 1988. And the design typically consists of a motor-driven screw which pushes a specified amount of powder into a chamber. This amount of powder is a function of the setup dimensions and the screw RPM. And once it is pushed, an inert gas is used to push and carry the powder forward. Again, should you want to use multiple powders, you can have multiple such assemblies which push or say carry the powder into a stirring chamber which produces a homogeneous or stoichiometric mixture as per your requirement. The second class of systems are based on vibratory methods, where we use mechanical vibrations to meter and transport this material. Such mechanisms are already commonly available in agriculture and food processing industries. However, they are not they have not been extensively used in metal additive manufacturing. Here we see an example where a radial vibration with a piezoelectric ring and a longitudinal vibration with a voice coil vibrator is used to say transport the powder which falls under the action of gravity from a hopper ahead into the region of interest. Another class of systems are based on gravity, and they just use plain old gravity for powder handling. However, these are not very commonly implemented And one of the reasons is because of jamming. And empirically, it has been found that should this uh, neck diameter, capital D, be of the order of 3 to 4 times the particle diameter, the particles will simply jam and not allow any further movement. So it has to be necessarily be greater than 3 to 4 times the particle size. These particles also that we see here are of uniform shape, but typically you will have a distribution, and there will be large and small particles. Such jamming may stop the granular flow for systems operating under gravity. The next class of methods for metering and convening are based on pneumatic techniques, and these are the most popular and commercially implemented methods. All commercially sold powder feed units employ this mechanism for powder metering, conveyance, and delivery. And that is a very strong statement because all systems use it. And such a pneumatic setup was developed exclusively for DET. So here you have this uh, index plate which has holes, and then you have the base plate which has only one hole, which is shown here. Now, depending on the RPM with which this index plate is rotating, there will be time windows when the hole in the index plate overlaps with the hole in the base plate. And during this short interaction window, the compressed inert gas is used to push the available powder in this hopper chamber out through the powder outlet. Now, if the angular velocity omega is increased, we can clearly see that the instances of overlap of the base plate hole with this index plate hole will be higher, and so more amount of powder will be expelled. If the index plate angular velocity is low, then low volume of powder will be transported. All pneumatic methods in principle work by creating a pressure difference. So either you can have, like in this case, a compressed inert gas and atmospheric pressure, or you may have atmospheric pressure and a vacuum, depending on the system. For pneumatic methods, there might be certain other designs, which, though popular, are not commercially implemented to that extent of the one we saw previously. So in one case, you may have a hopper through which powder falls out under the action of gravity, enters a groove of a rotating disc, and then a vacuum line pulls this powder out and deposits it into the necessary region. A second may have a metering wheel, which, through the interaction of carrier gases, again transports a requisite amount of or requisite quantity of powder into the desired region. Electrostatic methods may also be implemented because typically we are working with metallic powders. They will be electrically conductive, and electrostatic valves, if used in such systems, may be used to retard the free flow of particles from 50% to 3%. And the system is sensitive towards particles' electrical conductivity. And under the action of these electrostatic electrodes, there might be an accumulation of agglomerated powder inside the funnel or inside the channel, and with time, this might increase to narrow down this passage, thereby limiting the amount of powder which can pass through. The types of powder delivery system are summarized here. So you can have a lateral feed of powder similar to a lateral feed of wire from an off-axis nozzle that is shown in figure A here, or you can have a continuous coaxial feed of powder where the energy source is in the center and you have powder coming from all around it in an annular fashion. This annulus converges on the melt pool on the focal plane on the substrate, An approximation of this is where rather having this continuous coaxial type of hollow nozzle, you have some discrete nozzles which will be easier to say implement but act in a similar fashion. Or in the other case, you have the powder coming from the center and you have the energy beam coming from the sides. So again, either in the form of an annular laser or you can have multiple discrete lasers which again converge on the multi. As we see, in cases B, C, D, and E, the omnidirectionality is achieved. Whereas in case A, omnidirectionality is lacking. The off-axis nozzle, as we discussed, finds typical use in cladding of cylindrical surfaces as it has a very easy setup and design. It may lead to an asymmetry in powder temperature, laser intensity, and melt pool. However, they are still used for cylindrical components on rotary setups because of the ease of operation. Now, some typical designs of the continuous coaxial nozzles are presented here. And here we see that there are multiple channels. There is one channel at the top from which the inert gas is entering. And the purpose of this inert gas is to protect the optics. That is, if there were the bounce back of any particles from the surface or the reflection of any laser energy back into the laser optics, or certain fumes will be generated here. And to prevent the entry of these fumes back into the optics chamber, the inert gas is purged through these channels. The second channel is used by the powder and carrier gas to transfer the powder material for deposition. Again, we see that there is this reservoir here at the top, which may be used to compensate for any fluctuation in the amount of powder being carried. The third channel is used again for purging shielding gas. However, the purpose of this gas is the protection of the melt pool from the surrounding oxygen. So it acts as a shout gas and displaces oxygen. So because of the limitation of lateral feed nozzles, such as the lack of omnidirectionality, coaxial nozzles are commonly used in DD process, and they have this common generic design that we just discussed, and it has provisions for shield gas for the protection of laser optics from metal fumes and dust, passageways for a convergent powder stream, and the provision of shout gas for protection of the melt pool. Some other designs are also shown here, such as one which instead of purging the argon gas onto the melt pool, uses this blanket of gas. So, like a blanket of gas, which is transparent to the laser which is which is passing through, but stops the movement of any particles or fumes into the optics chamber. There may also be certain vacuum ports which are designed, which can help in recovery of some of the shield gas. As we discussed, the typical flow rates for argon can be, say, some 10 liter per minute to 30 liter per minute, or even more. And so we say that a very healthy amount of uh, what noble gases and inert gases are being used for the process. Also, depending on the part size, your build times will be very long. So we may end up expending a lot of amount of gas. Even if some part of it can be recovered, it may prove useful. Discrete coaxial nozzles use multiple, such as 3 or 4 jets of powder stream, and deliver feeds of directly into the melt pool via separate and distinct powder delivery channels. The inclination of these channels with respect to each other will affect the powder flow characteristics and shift the location of powder stream's focal point related to laser beam. The number of powder streams or channels which are participating has a significant influence on the stream characteristics and also on the catchment efficiency. Catchment efficiency is the fraction of powders which are actually getting entrapped or getting deposited into the milk pool. As we know, not all powders will enter the milk pool. Some may bounce off, some may be divergent and may not enter the milk pool at all. And only a fraction will actually end up getting deposited. Typically, that fraction may be anywhere from 30 to 80%, but not higher. This was all that was discussed in this week. The contents that follow are discussed in the upcoming week. So we will take a short break, and after that, we'll solve some illustrative problems, which will help us in solving the assignments for this week.
Hello, hello. Hello, is the meeting available going on?
Good evening and welcome back. In the chat, I see a question from Mr. Munshi. What is the impact of decreasing the work function phi of the metal on thermionic emission? Mr. Munshi, as far as I'm aware, the work function is actually a material property and it cannot be like tuned by us. So it is a function of the material that we are using. Typically for thermionic emission guns, we use tungsten or tantalum, which have very high melting points. And so they can be subjected to a great influx of energy before they start to melt. But whether the work function can be tuned or not, I'm not sure. But if you were to compare across materials which have different work functions, say one has less work function than the others, it implies that a lesser amount or a lower amount of energy is required to excite the electrons to come out from that target surface. Thus, if I had a choice of two materials, uh, one with lower work function and one with higher work function, all other factors remaining the same, we should opt for the one with lower work function because it would require less energy input for excitation of electrons. We'll continue with our question and answers. So the first question, sorry, which are the deciding factors in choosing optimum standoff distance in a blown powder DED process? A blown powder DED process is just one of the names for your typical powder-based DED. And here we are talking about the relative positions of a few things. So the focal point should be sufficiently away to prevent nozzle damage. So typically, your nozzles are made out of copper and they tend to have a life of say 4 to 6 hours. This is just a typical number, it might vary, and they get worn out by interaction of the wire or powder material with the nozzle. Also, by they get deformed and affected by the high temperatures of the process. Now, should the focal point be very close to the nozzle? So, this is my nozzle, and if my focal point is very close, the nozzle will be subjected to high temperatures, which may produce thermal deformation. Also, because of the very close distance, there is a high chance that whatever fumes or rebounding particles are generated, or the metal vapor which gets generated, it might ingress into the nozzle and thereby into the optic system. Also, the material is deposited here, and if there is certain fluctuation in the deposition characteristics, say you have a lot of deposition in one region, or as we discussed when we are depositing geometries, at the corners, typically you have more material deposited. So say I am depositing if my nozzle is there and moving in this direction, there might be a chance that because the Z height will be fixed, it may come in contact with this pre-deposited material which has bulged out at the corner and may even hit the nozzle. So the focal point should be sufficiently away to prevent nozzle damage. This is correct. The laser working zone should fall within the standoff distance. The standoff distance, as we know, is the distance of the nozzle or the tip of the nozzle from the substrate, and we want the working zone to fall within the standoff distance. The working zone is basically, informally, what we would say is it is the region within which interaction of the powder or wire and the laser will lead to sound deposition. So often because of the surface fluctuations or the deposition characteristics, the exact distance of the focal spot of the deposition region from the nozzle will not be fixed, as we saw. There might be some bulging at the corners, and this will lead to change in this distance. However, if it is still within a range which we call the working zone, the deposition will still be uh, more or less uniform and will end up with sound metallurgical bonding. You want this working zone to fall within the standoff distance. It should not extend beyond the substrate, say, or it should not be less than the standoff distance because then we lose out on useful area. So option B is also correct. The laser focal point or the waste radius should fall within the standoff distance. So the standoff distance is actually the distance between the substrate and the nozzle tip. So typically this. And as we saw in one of the schematics, the beam radius is encountered here. The beam radius, if you recollect, is the narrowest section of the laser, or the waste radius. And typically this falls with inside the nozzle itself, after which the beam again diverges. This beam radius typically will fall within the nozzle and this is outside the standoff distance. So option C is correct. The correct option, both A and B, option D. What are the reasons for difficulty in additive manufacturing of metals like copper and aluminum? They are highly reflective. This is correct. And a workaround is to, maybe roughen the surface of the sub-build plate to get rid of some of this high reflectivity. They have high thermal conductivity. This is perhaps the most debilitating reason. And what happens is when the substrate or the pre-built layer is bombarded with the energy beam, often rather than the localized rise of temperature, which may lead to melting, because of the high thermal conductivity, the energy is dissipated quicker than it is getting received. So while the bulk temperature of the material gets raised, there is no localized melting because in a local region, the heat is getting dissipated too quickly and there is simply not enough energy buildup for any melting to happen. Laser of suitable wavelength is not available. This is not true, and there are lasers of wavelengths, typically called blue lasers, which have been used for successfully printing copper. So they are available. Thus, the main difficulty lies in the high thermal conductivity and also the high reflectivity of the materials copper and aluminum. Option D. What is the drawback of utilizing a central feed with annular laser as a powder delivery system? So if we just recollect, the central feed with annular laser had the powder coming from the center and there was this annular region around it which the laser is coming. So also from the back here and from the center the powder is being fed. So and they combine together to form the melt pool. This powder also falls into the melt pool directly. So while the catchment efficiency is high, there might be some other drawbacks. And let us try to think what that is. Sophisticated optical systems are needed. This is true because you would have to convert your typical beam which comes from the lasing system will be at the EM00 beam. So maybe a circular cross section. The distribution of energy may be Gaussian or some other depending on the type of lasing system. You will have to first make it into annular or donut shaped beam using something called an axicon, an optical system which we just saw. And then it might also have to be split up and then joined again and further converged, which requires a lot of sophisticated optics. Low catchment efficiency, as we just saw, the catchment efficiency will be pretty high because Here, rather than being fed laterally, the powder is being fed axially and falls directly into the melt pool. Of course, there will be a small fraction which say bounces off the melt pool or which because of collision with other powder particles may get diverged, but a large fraction will definitely go into the melt pool. So catchment efficiency is good. Lack of fusion at the edges of the melt pool. This again is a characteristic of lateral feeding. That is when you have a lack of when you have powder coming from only one side and they call a lack of symmetry. In this case, there will be no preferential lack of fusion at any of the edges. Lack of fusion at the center of the melt pool as no energy reaches the center due to angular shape. This is also incorrect because if we were to take sections at various regions, so here the shape might be, uh, sorry, a larger annulus and keep on decreasing until at the melt pool itself, it will be a TM00 profile again. So there is fusion at the center. So option D is also wrong. The correct option is option A. It is because of the requirement of sophisticated optics. A student proposes the idea of blown powder directed energy deposition using an electron beam as the energy source. What advantage will this technology provide over laser-based blown powder directed energy deposition process? Will it have a lower cost? Will it have higher production speeds? Will it have lower porosity of finished parts? If you look at the question carefully, it says that the idea is of a blown powder directed energy deposition process using electron beam as the energy source. And when you are having electron beam as the energy source, we require a vacuum, if we recollect. So typically of the order of say 10 to the power minus 5 milliwatt in the working chamber, and of the order of 10 to the power minus 9 to even 10 to the power minus 10 milliwatt in the gun chamber. And whenever we bring this blown powder concept into the picture, blown powder implying that the powder will be carried using some carrier gas. It may be argon or nitrogen or any other inert gas. The ingress of this gas will lead to loss of the vacuum. And once the vacuum is lost, the electron beam based process cannot work well because electrons being very light particles, when they collide with these molecules of argon or nitrogen, they will simply get scattered and they will not reach the substrate or P layer to say transfer or transmit kinetic energy. So this process will simply not work at all. Thus the correct answer is D, none of the above, as the process is not feasible. Question 5. Why are off-axis nozzles preferred for cladding of cylindrical components on a rotary setup? So as we saw, there are instances where say you have a cylinder and you maybe want to coat some secondary material or some feature on top of it. So it is subjected to some rotary motion. And in such cases, we saw that often off-axis nozzles are used. But what can be the reason for such usage? Is it the lower cost? We're not really sure if the cost is lower. Most of the cost goes into the laser system, the optics, the collimators, uh, other stuff. Well, the powder or wire delivery system also incurs a significant portion of the costs. That alone itself is not enough to offset the costs and comparing one to as to having higher and the other being very cost effective. So cost is questionable, it is not definite. higher production speeds. As we know, the production speed will not be determined by the type of the uh, say delivery, whether it is lateral or coaxial. Rather, it will be the volume of auto delivered. So production speeds is not the correct answer. Deposition is occurring in only one direction, which is true because typically with this rotary motion, you are just depositing along the spiral path. Omnidirectionality is not a problem. So the deposition occurs in one path. So your simple lateral nozzles are suitable. All of the above not true at all, of course. So option C is correct. Why are inert gases such as argon used in powder feed additive manufacturing processes? Is it to shield the melt pool from atmospheric gases such as oxygen? Similar to welding? Yes, this is correct. Is it to deliver the powder feedstock to the melt pool? We discussed how these processes are blown powder type processes. That is, the powder will have to be carried into the melt pool by some carrier agent, and typically it will be your inert gas. So option B is also correct. To improve interlayer adhesion by improving surface tracking properties. If you remember, this is something we read in the slides, and this is true. To protect the laser optics, as during the deposition process, because of the melting and vaporization, metal fumes are formed, which may enter the laser optic system and may get deposited on the optics and harm their functioning. So, a shroud of argon gas, either in the form of a blanket or as a flowing converging stream, is used to protect the laser optics. So, this is a multi-option correct type question, and all the options are correct. What problems can be introduced by the use of inert gas for shielding the melt pool? Now, this is very tricky because just in the previous question, we were listing off the merits of having inert gas flowing into the system, and that too we had multiple channels for one for protecting the optics, one for delivery of the powder material, then another for shielding the melt pool from oxygen. But can it also have some inadvertent disadvantages, or is it all rosy and we can have an arbitrarily high volume of uh, argon or other inert gases flowing over the melt pool? Does it lead to the entrapment of gases? Yes, this happens. As we were discussing, the powder material itself may have been formed through an atomization process which may use water or some inert gas. Atomized powders typically use nitrogen or argon, and these may get entrapped into the powders. Additionally, the inert gas which flows over the melt pool may also get entrapped to a certain extent because we know that the solubility of gases in metals is higher in the liquid phase and lower in the solid phase. While it is still molten, the melt pool may dissolve some additional gases. Does it lead to turbulence in the molten liquid of the melt pool? Because the gas flows over the molten surface of the pool. So if we see a cross section of a melt pool, there will be some dilution. Now this top surface is free. That is, it will interact with the surroundings and may change its shape. Now, when the inert gas flows over it at significant volume rates, this leads to surface waves, which produce turbulence on the surface as well as may lead to turbulence in the bulk of the molten fluid and can disturb its characteristics. So option B is also correct. Does it lead to porosity in the printed part? We know that, say, common types of porosities or porosity defects are one where you have these almost spherical small pores, which are your typical gas porosities. Gases have a higher solubility in liquid metal when the metal solidifies. These gases can be liberated, such as hydrogen, and when they are liberated, they form such pores and may later escape. The second class of porosities are your elongated type with irregular morphologies, and these are your process-induced porosities, such as lack of fusion porosities. The first kind may be enhanced by the entrapment of inert gases into the melt pool as well. So this may excessive volume of gas interacting with the molten liquid may lead to porosity as well. So all of the above are true. The next question is asking us, why are wires with diameter less than 0.2 mm not preferred in laser-based metal wire additive manufacturing? Is it to obtain sufficiently high deposition rates? We know that the deposition rate is correlated to or is related to the volume of wire coming into the melt pool and melting there. If the diameter is very small, the volume flow rate, that is the wire feed speed times the cross section of the wire, will be very low, leading to insufficient deposition. One of the primary reasons of using wire-based processes is because of their superior deposition rates compared to powder-based processes. Thus, the deposition will be compromised. Is it to ensure that the feedstock wire travels into the molten pool? So what happens is, typically your wire will be, say, in the form of a spool, and it will be under tension, of course, and it will be unwound from the spool and fed into your uh, deposition system. Now, typically you want your wire to flow directly into this milk pool. But realistically, what happens is, because it is coming out of a spool, it will also retain some of the curvature of the spool. And if it is very slender, that curvature may be very pronounced. And thus, it might not get fed into the milk pool at all. Especially if the wire is very slender or very thin, that is, it has a very small diameter, this curvature can be highly pronounced. So to ensure that the feedstock wire travels into the molten pool, we should avoid very thin wires. Is it to ensure that the wire does not melt prematurely above the laser focus? So typically, your wire will interact with the laser either in the form of in the three cases that we saw, whether a bridge transfer or stubbing or a droplet transfer. While the diameter does affect the surface area and thereby the amount of energy that the wire can uptake, still it is a process parameter which can be adjusted, as we saw that the critical distance can be a function of the radius. So this by itself is not really a drawback, and it can be adjusted in the process parameters. So option D, that is both options A and B, are correct. The next question. The process map corresponding to Inconel 625 wire having a radius of 0.7 mm is shown in figure 1. For a laser power of 0.85 kilowatt, that is 850 watts, traverse speed of 1.7 millimeter per second, and wire feed rate of 10 millimeter per second, what will be the wire deposition characteristics? And based on the process map, we have to comment what type of deposition it will be. So typically you have this dripping region, transition between dripping and smooth wire flow or bridge transfer, transition between smooth and stubbing, and region of stubbing. So if we can locate the coordinates of our process on this process map, we'll be able to comment on what this region is. So let us just write down whatever parameters are available to us. The radius of the wire is given, it is 0.7 mm. The power is 0.85 kilowatt, which is 850 watts. The traverse speed, say if we denote it by Vt, is 1.7 millimeter per second, and the wire feet rate, uh, if we denote it by Vw, in as per the notation of the slides, it is given as 10 mm per second. Now, the formula for the linear energy density and the deposition volume per unit length are already available with us from the slides. We'll just apply them directly. The linear energy density is given by power by traverse speed. The power was 850 watts, 850 joule per second by traverse speed Vt, which was 1.7 millimeter per second. I'll just calculate this. This comes out to be 500 joule per millimeter. Next, the deposition volume per unit length of track. First is area of the cross section of the wire, which will be pi d square by 4. D is 0.7. Or okay, we have pi r square. So pi 0.7 square with a unit of millimeter square times VW or the wire feed rate. VW is 10 mm per second by Vt, which we have previously used as 1.7 mm per second. And we can just calculate this quickly. 0.7 into 0.7 into 10 divided by 1.7. This comes out to be equal to 9.055, and the units, if you notice, given here is millimeter cube per millimeter. So we'll retain this one, millimeter cube per millimeter. The reason for this units is because it is given as the deposition volume per unit length of track. So it's a volume millimeter cube per unit length, which is millimeter. So now we have our coordinates. Here along the x-axis is the volume per unit length of track. So x is 9.055 and y is the energy per unit length of track, which is 500. This is our process coordinate, and let us try to locate it on this graph here. So 500 is here. 9.055 is almost equal to 9, so somewhere here. And this is the location of our process point. And we see that based on the given process map, this falls in region 5, which coincides with the stubbing region, the region of stubbing. So we can say that for our process as well, stubbing occurs. This is not optimal. That was it. I see another question in the chat. This is also from Mr. Munshi. In case of lateral feed powder delivery nozzle, depositing uniform tracks while cladding of cylindrical workpiece on rotary axis, primarily because of what reason? So the problems with Uh, the problems with lateral powder feed occurs only in the case of change of the direction of travel, and that is because of the lack of omnidirectionality, as we saw last week. You can have front deposition, side deposition, back deposition, and so on, back feeding, and so on. In the case of deposition in a spiral path on a cylinder, your path or your deposition direction is not really changing. You're always depositing, say, in the front feeding mode only. So there is no problem. It is as good as any other process which may have omnidirectionality. And given that it is the easiest and oldest implemented type, you can save a lot of cost by implementing it. So it is still preferred for such simple applications as the cladding of cylindrical workpieces on rotary axis. So thanks for tuning in. That was week 9 of the live sessions for fundamentals of additive manufacturing technologies. I thank you for your patience and hope to see you all again next week.
Thank you, sir.